Today we're going to be looking at compound interest and continuous growth. So interest is an amount that is paid or charged based on the amount of money invested or borrowed. We calculate interest with a percentage rate, and we can calculate it two ways. The first is simple interest, which is a set percentage that is calculated one time per year on your principal amount, or the deposit or the amount borrowed. That's our principal amount. Or we can calculate compound interest, which is calculated on the principal amount plus anything else that has been deposited into the account, meaning if I earn interest after 3 months, then at 6 months I would get to collect interest on that interest. And we're going to calculate that more than one time per year. So these are exponential growth functions, but we have to write them a little bit differently because of the way that the interest is calculated. So this is our general formula for compound interest. A is our final amount after the interest has been calculated. P represents the original amount that's deposited into the account. R is the interest rate as a decimal. And notice that we have to divide that interest rate by n, which is the number of compoundings in the year. So if we wanted to see what our actual interest rate is, we would take r and divide it by n. And then we also have to change our exponent because we are compounding the interest more than one time per year. We would have to take that number of compoundings and multiply it by t, which is time, usually in years, to get our exponent. So everything here should look similar to our exponential growth formula other than the change to the rate and the change to the time. So ways that banks can compound interest would be annually. So that, again, that's our simple interest, just one time per year. They could compound semi-annually, which is twice. Quarterly is 4, monthly is 12, weekly is 52, and daily is 365. So an example would be $1,500 deposited in a bank, paying an annual interest rate of 4.3% compounded quarterly, and then they ask what is the balance after 6 years. So the key information that we're looking for is the amount deposited, so $1,500. We need to identify our interest rate at 4.3%. We need to figure out what our compounding end value is, so in this example it's quarterly, and our time is going to be after 6 years because that's when they want to know what the balance is going to be for after that set amount of time. So we take our general formula and we plug in these key values. When I work these problems on the calculator, oftentimes I will go ahead and do the r divided by n and then add 1 just to make sure that the calculator is following the order of operations correctly. And you'll notice here that we have 4 times 6 in the exponent. So again, 4 is from the quarterly compounding. So 4 times per year for 6 years, which is t, results in this exponent of 24. So we take and raise that interest rate to 24, multiply it by the original deposit of $1,500. So after 6 years, I would have an account balance of $1,938.84. Next example, Jerry deposits $1,200 in an account paying 9% interest compounded monthly. How much interest will he earn after 20 years? And we're going to assume that he's not making any additional deposits or withdrawals. There's a much more complicated formula that we don't cover in this course when we keep adding money beyond the interest or taking money out. So again, our key numbers here are $1,200, so that's what he's depositing, that's P. A 9% interest rate is going to be compounded monthly, so N is going to be equal to 12 because there's 12 months in a year. And we want to know how much interest he's going to earn after 20 years. Now notice that this question is different than what is the balance of the account. Now we just want to know just how much they're adding in interest. So there's going to be an additional step in this problem. So again, we start with our compound interest formula. We plug in our key values in for all of our variables, and then we start our simplification process. So he's going to have this interest compounded 240 times in 20 years. So after those calculations are finished, we see that his account balance is going to be $7,210.98. So that's a pretty hefty increase in the account balance. But we just want to know the interest, so we have to subtract that original $1,200 deposit to see that the interest is going to be $6,010.98. So how much money would you have if you invested $1 at 100% interest compounded at all of these different rates? So this would be a formula that is going to look like this. So if we get our drawing tool open here. So I would say that I had $1. I'm keeping 100% of that dollar. I'm adding another 100% interest raised to the t power. So this is really more like a doubling example with that first one. With semi-annually, we would have to divide the 1 by 2. With quarterly, it would be with a 4. So if we were calculating interest once every second, so 31,536,000 times in 1 year, I feel like I would have a pretty good amount of money. But the reality is, when we look at the actual computations, my amounts aren't changing as much as I thought that they would. I mean, now we're down to like pennies difference. And then the more often that we compound that, it's not really changing at all. I seem to be stuck at this 2.71 number. If we think about how often every second would be, that would be like we're just constantly calculating interest. Which leads us into our next type of growth, which is continuous growth. So the value is constantly changing. This would be faster than being compounded every second. But what happens is that we kind of get stuck there. And the number that we were looking at in the previous example was Euler's number. It's an irrational number. It's like pi. It's about 2.71. And because we know that this number is going to occur when we're constantly changing and constantly compounding, we actually use that number as part of our formula, and it changes our formula. So you have to be explicitly told that the situation is occurring or compounding continuously or changing continuously to use this formula, which is A equals P times E raised to the power of R times T. Now, because E is an irrational number, your calculator has this pre-programmed in to be able to calculate with. So you would look on your calculator and find, it looks like an italicized E, which is representing that Euler's number. Sometimes in science we call this the Pert Formula because population growth, so things like when you look at ecology and life cycles, we're going to use the Pert Formula to help us model how our population is changing within an ecological system. So you do need to recognize when to use this formula, again, by using the word or looking for the word continuously. So it might look something like this. Suppose you have $12,000 to invest. Which investment yields a greater return over 3 years? 7% compounded monthly or 6.85% compounded continuously? So our key phrases again, our key numbers are $12,000. Time is going to be 3 years. We're actually working two problems here. We want to look at 7% compounded monthly, so we're going back to that compound interest formula. or 6.85% compounded continuously. So often students try to combine these two or use the formula in the wrong place. So again, paying attention to the words and the context is key. So for 7% compounded monthly, again, we take our investment, which is $12,000, our 7% interest rate divided by 12 because we're compounding monthly. Our time is 3 years times 12, so an exponent of 36. And once we're done with that calculation, we would see that our investment would yield $14,795.11. A different example would be that they want to know if it's compounded continuously. So rather than dividing the rate or anything like that, it becomes part of the exponent. And I don't have to worry about compoundings because this is happening all the time, which is why we use our base e. So 12,000 times e raised to the power of 0.0685, so taking the percent, still changing it to a decimal, times 3, which is t, the number of years, calculating that number, multiplying it by 12,000, and my yield would be $14,737.67. So again, our kind of human nature is, if it's happening continuously, it's got to be the better result, which we see is not really always true. In this case, we're going to get a better return if we are taking our 7% compounded monthly over 3 years.